14.2. Recall that when we integrate over a rectangular region, the order of integration does not matter. Suppose our region is bounded above and below by functions of x. In that case, we want to slice perpendicular to the x-axis. And our double integral is done this way. On the other hand, if the region is bounded by functions of y, we slice perpendicular to the y-axis and do the double integral this way. Find the volume of the surface over the general region. First, think about which way we're going to slice this. We have y written as a function of x. With a function of x, we slice perpendicular to the x-axis. We have found the bounds on y that was given to us. What are the bounds on x? By looking at points of intersection, we can see that the bounds of x are -2 and 2. And we are ready to integrate. We need to evaluate this, and we're left with an integration of just one variable. Finish this up. Doable but rather tedious. If the region is bounded above and below and on the right and on the left by curves, we can choose either order of integration. However, as in the example below, one order of integration may be preferable. The way given is certainly not preferred. Perhaps changing the order of integration is both possible and useful. Currently, we have x written as a function of y, and we are slicing perpendicular to the y-axis. Perhaps we can change that. Viewing y as a function of x and slicing perpendicular to the x-axis, we get that the region R is bounded above by y equals x and below by y equals 0. And we have successfully changed our order of integration. Integrate the inner integral. And evaluate. Once you evaluate, you can see the benefit of the change of order. I have sine of x squared, and so when I do my u substitution, u equals x squared, I've got the x that I need to do that substitution successfully. If we had done the integral the other way, we would not have this piece to allow us to do a substitution. Our last step is to integrate and evaluate this integral. And because of our order, that's a fairly straightforward process. Find the volume of the solid region bounded by the paraboloids. The blue paraboloid is z equals x squared plus y squared. To find the region over which we are integrating, we need to find the x and y values for which the paraboloids intersect. So we set the paraboloids equal to each other. And when we do that, we see the curve that describes the intersection is a circle of radius 2, centered at the origin. We are now ready to describe R. Depending on which way we want to slice the solid, we will either write y as a function of x or vice versa. Looking at the surfaces, we see it doesn't matter in terms of the integrand. The difficulty of the problem is the same either way. The traditional choice, when it does not matter, is to choose y as a function of x. In that case, we're slicing perpendicular to the x-axis. So we write our region this way. Y, the bounds on y are written as functions of x, and x is just going to vary from -2 to 2. Next, let's use symmetry to simplify our double integral. We will want to find the volume of the entire solid. What we will do is we will find the volume of the solid just in the first quadrant and multiply our answer by 4. This not only reduces the complexity of the problem, it decreases our chance of error. So we've got it multiplied by 4, and you can see that we're staying in the first quadrant. And this is the problem finished up. It's a very brief overview. I'm not showing you the grunt work. I'm not showing you the trig substitution. I skipped a lot of legwork. You can see your book for more details and let me know if you have questions. But when we get to polar coordinates in the next section, you will wonder why you even bothered. I'll see you then.